Okay, good afternoon, ladies and gentlemen. Thank you for joining us today regarding visiting lecture, the lecturer program with Oles Honchar Dnipro National University from Ukraine. Welcome to the Honorable Mr. Olexander Trofimov, as an Associate Professor of Department of Computational Mathematics and Mathematical Cybernetics, candidate of Science, Physics, and Mathematics with us today. And also to all participants today, today's session is being live streamed on the Universitas STEKOM YouTube channel. And now I will read our agenda this afternoon. First, we will start with class presentation by Mr. Olexander Trofimov. On the topic today is block-parametric approach to non-destructive control data analysis of layer foundation, and continue with the Q&A session for all participants in the next session. If you have any question for the speaker, please add them to the chat or you can raise your hand. Your question will be answered after the presentation, and we will go to continue with the time for documentation. And last is a closing. And let's start our class today for Mr. Alexander. The time is yours. Thank you.
Thank you very much. I am glad to meet you and to see you. And let's begin our presentation. Okay, I am Alexander Trofimov. I'm associate professor in Dnipro State University, Dnipro National University, Oles Honchar. I am working in Department of Physics and Mathematics and Computational Mathematics. Also, I am a Master of Science in Transportation Engineering and Logistics. And my main direction of interest are inverse problems, numerical methods in engineering and natural sciences like mechanics, physics, and others, theory of optimization and optimization in logistics and transportation technologies, and methods of non-destructive control of structures and its elements. Now, the topic of our lecture is block-parametric approach to non-destructive control data analysis of railroad layered foundation, but not only railroad, but in all similar structures in several fields of transportation. For example, in automobile transportation, for example, pavement structures and others. What is the main purpose of our work? Main purpose of our work is to investigate the methods of non-destructive control data analysis that we may collect from testing the element of structures of transportation communications. The evaluation of parameters of multi-layered foundation, for example, pavement, runway, strips, and others, ballast prisons in railway transportation plays a very important role in ensuring the safe movement of vehicles. our approach of model construction for estimating the mechanical and geometric parameters of such foundations based on the solution of inverse problems for multi-layered elastic and elastoplastic packets. This method allows to recognize the weakness of the structures and prevent unallowable deformation and destruction of them, and thus increase the safety of transportation traffic. The method of obtaining the diagnostic parameters for road bed structures are like this. There are engineering and geodetic, ground penetration radars, methods of loading trains, and commonly method of loading trucks and other vehicles. Methods of measuring the surface point elastic displacement of the roadbed structure under the passing trains, and the seismic methods. For example, in this picture, we can see how the methods of measuring the some displacement, elastic displacement in the roadbed structures are realized. We see that we assemble the structures consisting of the set of scanners that placed on the certain points of ballast prism or other parts of layered foundation. And after the trains passed, we can collect the information of displacements in these points and treat this information and obtain some data for mechanical parameters of these foundations. Ground penetration radars use the georadars determining geometric characteristics of multi-layered foundations that form in the pavement and other structures, and as well as some physical characteristics, but in implicit ways, such as, for example, moisture content, porosity, density, and others parameters that are directly or indirectly can affect the strength of the considered structures. These methods use the radiation for forming the signals for such data. The next type of methods is, for example, falling weight deflectometers, is the equipment that can measure the displacement or velocities of some points of the surface under the act of heavy plate that falling from a certain height and make a disturbance and waves in the media of the foundation. It's a very old equipment, but it's very precise and compact. In this picture, we can see that this equipment can be moved by a small car or pickup. But existing methods have some shortcomings. One of the main shortcomings is, for example, for engineering and geodetic methods, high informativity, but long duration and a high cost of the process of measuring and collecting the data. Like this, it's a very expensive and have a long time to collect this system of testing the roadbed structures. Some methods have high speed and low cost, but a low informativity. For example, ground penetration radars don't collect the explicit information about the mechanical parameters of the tested media. For example, modulus of elasticity, Poisson ratio, and others. Only implicit data can be collected, such as porosity, coefficient of porosity, density, and others. And the common problem is a low level of data interconnection. It is very important to combine the data collected from different sources. For example, displacement of some points over moving load and data from, for example, penetration radars and maybe other sources of information. But in the present decades, some modern equipment, advanced and sophisticated equipment had designed. For example, in this picture we can see the traffic speed deflectometer designed by American corporation. It's a heavy truck equipped by the system of scanners that can registrate the displacement or velocities of some points under the moving load by moving this track. Similar equipment have been designed by European engineers in Denmark, named Dynaset Raptor Roland Wheel deflectometers. The principles of scanning we can see in the lower picture. The scanning sensors may be assembled like this, perpendicular to the tested surface, and may be assembled like that under some angles in order to increase the informativity of the data and to obtain as more information as possible to solve our main problem of obtaining the parameters of mechanical parameters of the tested foundation. We can collect information about displacement like this and about velocities of these points using the principles of Doppler effect like this. This effect is the changes of frequency of the radiation, for example, light radiation, for moving objects. This reflected ray of the laser can be analyzed and this information may be analyzed and we may obtain the velocity of the moving surface or some point of the moving surface. On this picture, we can see the wagon or locomotive and the assembled system of scanning sensors that can scan the velocities of or displacement of tested ballast prism or other foundation. And what parameter of interest in the testing process of these structures? The parameters is like that. The geometric parameters, for example, the form of the surface that divide two different layers. And to divide the layered packet with ground foundation. Mechanical properties of the packet layers. For example, like elastic modulus, Poisson ratio, and others. Other physical parameters of layered material, porosity, density, and others. Properties of interaction between layers. How the packet layers can interact among each other. This includes, for example, the fraction ratio or information about how to interact, may interact which is other the neighbor layers. For example, then they can be glued or strictly connected, or may slip along each other. Properties of the ground subgrade. Subgrade is the base under that this construction lays, and the parameters of the distributed load. It's not easy to obtain the precise information about how is this load distributed over the set of the contact of this load. And which mathematical and mechanical models should we use to model this process? This model includes the equilibrium equations that can be written in displacements or in velocities. In these pictures, this is example of velocity formulations. So-called determining equations that connects stresses and deformations. Cauchy equations that connects deformations and velocities or displacements. Boundary conditions include the conditions on part of the surface where the load applied. For example, at the top surface of the packet, and some equations that demonstrate the interaction between packet and the ground subgrade, in this slide we can see. This equation demonstrates the so-called Winkler subgrade model that include only one coefficient of interaction, and may be considered the Winkler-Pasternak foundation that include two similar coefficients. Layer-to-layer interface include gluing conditions, gluing equations, strictly connected layers, and connections that may depict the slipping according to Amonton-Coulon law, for example. And in the particular case, the free slipping of the interacting surfaces on each other. And we consider this the element of so-called forward problem. Forward problem is the problem when the input data is mechanical characteristics of the media of the layered packet, mechanical parameters, and applied load. and applied load, and certainly the geometrically form of the layered packet. And the output data is the stress field and displacement field distributed on the over their this media. In mathematical language, we might determine the mapping from the space of the parameters of the foundation into the parameters of, for example, distributed field of displacement or distributed field of velocities in all point of this porous packet media. Model data vector is for example, displacement and or maybe velocities of displacements in the certain point of the top surface of this packet that we can scan by specialized sensors like that. This is a forward problem. And inverse problem is inverse mapping G months wine is the mapping from data space to the parameter space. Data space consists of the data that we can collect from scanning sensors. This data may consist of ray displacements or ray velocities on certain point over of the top surface of this packet. Forward problems is very known and very investigated, greatly investigated problem, but inverse problems is very difficult and not very not greatly investigated in some now. What is the classification of inverse problems in the common theory? Now, inverse problems can be divided into two classes. For example, regression and classification problems, and so-called properly inverse problems. As far as we know, there are two types of mathematical models to model the, for example, physical, mechanicals, and other processes. Empirical models or surrogate models, and theoretical or meaningful models. The examples of empiricals or surrogate models are, for example, linear regression model or model for time series. For example, ARIMA, ARMA, ARIMA models and others. And neural network models also belongs to empirical or surrogate models. And theoretical or meaningful models includes some features of the model process and might have a greater forecast possibilities. Empirical models are mainly common models, and theoretical is more specificals and therefore have greater forecasting properties. And we will have we consider in our investigation mainly the properly inverse problems that have the source from models of physical and mechanical processes. What is the element of the inverse problems? Elements of inverse problems are the first, a hypothetical class of models. Class of models determines the equations that we can consider to model this physical or mechanical process. And every such model or such class of model have some model parameters or factors. In our case, these parameters are like this: geometric parameters, physical parameters, mechanicals, parameters of interaction, and others. All these parameters belong to the space of the model parameters. The third element of inverse problems is a mapping characterizing a forward problem. Forward problem, in other words, forward problem operator. This forward problem operator map the data from the parameter space to the data in the data space HD, like this. Observation data is, for example, in our case, is the data collected from scanning sensors, and maybe other data that can be collected by other ways. For example, data from ground penetration radars, data of temperature, electromagnetic fields, and others maybe data. Noise is a characteristic of the imperfection of the observational data. The main features of the inverse problems are how to decrease the influence of the noise on the solution of this problem. Model data, we already considered this, is data that can be obtained from the certain parameter point is a parameter space that mapped by R mapping into the data space. And the process of solving the inverse problems is the fitting the model data to observational data. And these problems means in the artificial intelligence field like machine learning problem or model learning problem, finding the inverse operator to the operator of the forward problem. As far as we know, the forward problem is the key part of the inverse problem analysis. And to solve these problems is the half of the work to great is a half part of the whole work. Which methods can be used for solving the forward problems? These problems consist of two parts, the discretization process and the solving process of algebraic equations or other equations that we can obtain after the discretization process. In this picture, we can see the grid obtained by the sum process of discretization. Which methods can be used to discretize these problems? It's mainly the finite element methods and finite difference methods. Finite element methods have a variational formulation, and finite difference methods have difference formulations. In both cases, we obtain the systems of equations that might be solved by some methods. One of the most effective methods for solving such systems of equations is multi-grid iterative methods or multi-grid iterative algorithms. The main idea of these algorithms is to solve our problems not at one similar grid, but on the consequences of grids with smaller and smaller grid size h. We may solve the problem on the coarsest grid that have a small number of nodes, and then we can use these solutions as a first approximation of solving the problem on the finer grid with smaller grid size. This method consists of two parts: the so-called coarse grid correction algorithms and full multi-grid algorithm. Coarse grid correction algorithms uses the means of coarser grids to improve the solution on the certain grid. The main part of this algorithm is, for example, is a so-called relaxation process. Consists of smoothing iterations, pre-smoothing and post-smoothing. projection procedure of the residual into the coarser grid, coarser grid correction in the coarser grid, and interpolation the error to the finer grid, and then calculations in new approach and post-smoothing step. And the second part of the multigrid is so-called full multigrid algorithm. This full multigrid algorithm consists of the solving our problem on the coarsest grid with step size HO, the coarsest grid, and then use these solutions as an initial approximation to the solution on the finer grid. And in the cycle, we can achieve the finest grid HK. There are some parameters of this algorithm to be tuned in order to achieve the optimal efficiency of these algorithms. These parameters are number of smoothing iterations, of pre-smoothing or post-smoothing. In this picture, we see the same number, but in common case, we maybe differ. Projection procedure that depends of the way of coarsening. For example, the simple coarsening and semi-coarsening only in certain direction. For example, in X direction. And interpolation procedure from the coarser grid to the finer grid. In manner realization of the multigrid algorithm, these parts are more or less standard, but we can tune the number of smoothing iteration in order to improve our solution. And the next parameter is how many times can we use this procedure formulated recursively like this on the lower levels of grid to achieve the level of error that we can want. The structure of this multigrid may be determined by V cycle and W cycle and F cycle that differ from each other by the number of coarse grid correction iteration on the coarser level. And some type of analysis to tune this algorithm can be used. The old methods consist of local Fourier analysis for this goal. And in practice, we use the developed procedures of such methods, such iterations, such relaxation schemes and other parts of the multigrid algorithm and solving the model problems to obtain the optimal values of tuning parameters of these algorithms. In our work, we analyzed the problem and may select the robust scheme, geometrically robust scheme, to obtain the parameters called error reduction factor rho. That this factor means that we can increase the value of the error from the previous iteration to the next iteration. How this error may decrease. The smaller this parameters, the more effective is our algorithm. And it is enough only 3 iterations of coarse grid correction algorithms in the whole FMGS cycle algorithm. In the step B2, we improve the initial approximation, but by using several times the coarse grid correction algorithms. Several times means that, for example, 3 times is sufficient for efficiently solving these equations. And what is the difficulties for inverse problem solving? Mapping from parameters data space into the data space may not be a homomorphism, so-called the mapping that is not a surjection. So the mapping from the whole space not equal to HD. For some D observed, the corresponding inverse mapping may not exist. For some D observed, in HD may exist 2 elements for which these elements maps into the same point D observed. No, like this. For example, for this point DO in the data space, there is not the point in the parameter space that corresponds to these points by the mapping G. And the second difficulty, 2 points, M1 and M2, can map into the same point D1 in the data space. That's why the inverse mapping can be multi-valued mapping. And the third difficulty, for noisy data and exact data, the corresponding inverse mapping of these points may significantly differ, like in the this picture. For example, these points in the data space is close to each other, and in the parameter space, the correspondent submappings may be not very close, maybe on the long distance on each other. In the beginning of the 20th century, the principles of the correctnesses of the problems have been proposed by French mathematicians Jacques Adamar. These principles are like that. The problems is understood as the mapping of a certain set of factors into a set of indicators. The problem is called correct according to Adamar if first the solution of the problem exists for any value of the factors in the defined set. The solution to the problem is unique. And third, the solution of the problem continuously depend on the input data in a certain topology. The three principles: existence, uniqueness, and continuous. Like that. Correct problem includes that solution exists, unique, and continuously depend on the input data. And what is incorrectness? Incorrectness means that the sum of these principles are violated. Homeomorphism is a one-to-one correspondent mapping, bijections, and mutually continuous mapping that continues in one side from HM to HD and to the other side from HD to HM. Violation of homomorphism conditions for real mapping. Depict on these pictures. What is the main sources of the incorrectness of for inverse problems? The mapping of the forward problem is not necessarily a bijection, a surjection, excuse me. That's there is an element in the set of data that has no correspondence in the set of parameters. The first example of this in the top part of these pictures. The representation of the forward problem GM is not necessarily an injection. That's one of the same and the same element of data may correspond to more than one element in the set of parameters, like that in this example. M1 and M2 have the same correspondent element D1. Violation of the continuity of the inverse mapping. There are two main approaches to not avoid, but to work with the incorrectnesses. This concept consists of the deterministic inference and information probabilistic or Bayesian inference. Deterministic inference historically was the first from late 1940s to the present time. In this approach, it is postulated the solution of inverse problems objectively exists. In these problems, we have as input data HM parameter space, C a feasible set of parameters. In such parameters could not be considered in the real problems. For example, Poisson ratio in the real media could not be greater than 1/2 and less than month's wine, and others. Examples can be exist. HD observed data space, forward mapping GM, mapping from HM to HD, and observational data that needs to be inverted. The mapping GM is considered unambiguous, and the exact the described process or phenomenon being modeled. Objectively, there is an exact value of the indicator D, and D observed is D plus epsilon, means a noisy value. The value of the noise is not exactly known. There are certain estimates for its correct values. In this problem, we should find the inverse mapping from IHD to HM. The classics of this approach are Andrei Tikhonov, is a Soviet mathematician that popularized this approach from late 1950s to 1990s, and professor of Paris University, Guy Chaven, born in 1942. What is the main idea to overcoming the main sources of incorrectness of the inverse problem is in this deterministic approach. If there is no pre-image for a certain point D, O, then we will consider the point D or D1, which is the projection of the point onto the set GM like this. That's why if we have a point DO that have no pre-image in HM, we simply projected. We may simply project this element to the nearest point of in the data space where such pre-image exists. For example, point D01. This overcomes the first violation of correctness. violations that the solution of the problem exists for any values. The next, then the problems of optimization arises. We must decrease the norm of the GM months DO. At the same time, the first difficulty is overcome, and the other two remains. The behavior of these problems determines by the properties of so-called compact operators. In our problem or similar physical problems, these processes depicted by compact operators. Compact operator is an operator that maps the Banach space into itself if it transforms every bounded set into the relatively compact set. A set is called relatively compact or compact with respect to the space H if its closure in H is compact. A compact space is a topological space such that for any of its open coverings, there is a finite subcovering. And our aim, our goal is to obtain the inverse to the compact operator. And the problem that can arise from this determines the Schmidt's theorem for compact operator. Schmidt's theorem depicts the main mechanism of increasing the noise component of in the data space from mapping from the data space to the parameter space. The main mechanism is like that. We can determine the basis in the data space and in the parameter space. And this these elements of these basics have different frequencies. For in this picture, we can see the lowest frequencies and higher frequencies. And compact operators act like that decrease the amplitude of high frequencies components of the data, high frequencies, and low frequencies, amplitude of lower frequencies is not decrease greatly. Philosophical sense of compact operator. Compact operator maps supreme entity to inferior entity. For example, velocity displacement is a compact operator called integration. The inverse operation to this compact operator, displacement into velocities, this operator is differentiation, and it's lead to incorrect problems according to Adamar principle. For example, the classical example of this arising the incorrectnesses in the inverse of the compact operator is like that. The formula of, for example, right first derivative. The total error of this formula consists of two parts: the so-called truncation error and so-called computation error. How to overcome this this difficulty, this incorrectness? The regularization methods have been proposed. Regularization is a complex method aimed to overcome the second and third Adamar conditions violation by the restrictions of variation set of inverse problem parameters M. The set C determines the certain limits of physical variation, whereas the set HM the functional ones. Regularizations consist may be classified into two parts: functional regularization and physical regularization. Regularization method related to limiting the functional variation of parameters, extra requirements for the smoothness of the desired function M in case of a functional space HM, dimensionality reduction of the finite dimensional space HM, regularization by filtering, and interratio regularization. Regularization methods related to limiting the functional variation of parameters include the certain a priori information regarding a possible change in the unknown parameters, including the previous knowledge about this parameter. A priori information is information about the object under investigation, which is not directly related to the observational data of the current task. As a rule, this information is obtained prior to the consideration of these tasks through certain studies, regardless of the current task. Practice shows that the involvement of a priori information contributes to improvement of the quality of the analysis of the current task. This methods of realization can be considered as the particular case of penalty function optimization. Solving the inverse problems is defined as a minimization process of a functional created as a sum of two functionals. For example, residual. In this picture, we can see these parts: residual or fitting functional, and regularizing or stabilizing or prior functional. And alpha is the parameter of regularization. The most using regularization methods is Levenberg, Marquardt, Tikhonov. that proposed in late 1930s. In this method, the regularization functional omega have the form like that function psi is a non-decreasing function of x. That the problem can be written in the form of the optimization problem. Bayesian approach concept firstly was proposed in late 1960s, and this its main points of this problem, these concepts are like that. The exact value of the solution of inverse problems does not exist due to the lack of information about the exact values and the characteristics of the process model, so-called model uncertainties. Input data for the problems of, in this formulation are the prior probability distribution of the value of m in the set of parameters, certain assumptions about the values of m obtained independently of the assumption about the model of the process under consideration, and likelihood of the model. Likelihood means how likely the observed data correspond to the values in the set of parameters according to the model under consideration. This distribution takes into account both measurement uncertainties and modeling uncertainties. The classic of this approach was Albert Tarantola. He belongs to French mathematical schools of inverse problem analysis. What is the solution of inverse problems in the Bayesian approach? The solution of inverse problems is so-called posterior probability distribution, not a point of in the parameter space like in deterministic approach, but the function probability distribution, so-called posterior distribution in the set of parameters, which corresponds to the specified a priori distribution, taking into account the information about the observational data and the used process model, and is obtained as a logical conjunction of the prior distribution and the likelihood distribution. This statement is called the Bayes theorem. So the input data for this inference is theoretical probability distribution, a priori probability distribution, and the output data is posterior probability density sigma, determined like this. This is a Bayesian theorem or formula by Tarantola-Wallet. That's philosophical meaning of the Bayesian inversion, like this. Actual data analysis and prior information can be combined by Bayesian inference, and we obtain new knowledge for this combination. That's the example of using these Bayesian principles. This is a prior information, and this is a likelihood. And combining these distributions by simple conjunction operation, we obtain the posterior distributions and may investigate these properties of this solution. Important particular cases of this approach. Particular case that the distributions in the space MD can be divided into two parts, rho M and rho D, that M and D may be independent from each other. And the mutual probability that depict the likelihood may be written like that. And in the case of Gaussian modelization and observation uncertainties, this probability density may be written like that, and correspondent covariance matrix can be obtained by the sum of covariance matrix of modelization and observation uncertainties. The solution in the Bayesian prose is always correct because of the uniqueness of the input data, a priori probability density, and likelihood probability, and continuous mapping, continuous operation of continuous conjunction operation leads to the correctness by Adamar, the solution of the inverse problems, where the solution means the posterior probability distribution. And the main problem in this approach, it is simple to obtain the posterior probability by the simple operation conjunction, but it is very difficult to obtain the information from the posterior. And the main sense of the modern theories concerning the Bayesian inference is the methods of analysis for obtaining the sum information for forecasting of the phenomenon or process under investigation from the posterior probability and density. And with that, the correctness of the term solving the inverse problems. Whereas the solution of the inverse problem in Bayesian approach is the posterior probability density that is obtained in a straightforward way, conjunction operation. And the main difficulty is the extracting the useful information from the posterior. It makes sense to use the term analyzing of the solution of inverse problems or investigation of inverse problems instead of term solving the inverse problems. The main directions of this approach is optimization, uncertainty quantification, and uncertainty propagation. Optimization means that we can find the point in the parameter space that corresponds the maximum of posterior probability density. But maximum probability density is not enough for the practical purposes. Uncertainty quantifications investigates the behavior of the function of posterior probability in closure of the optimal posterior hypothesis point. And uncertainty propagations investigate how the uncertainty of the data influence of the uncertainty of parameters. This called inverse uncertainty propagations and forward uncertainty propagations, how to uncertainties in parameters influence to the parameters of in the data space. Like this in these pictures. The main purposes for inverse problem solving in Bayesian concept. First problems to check the validity of the parameters in input probability distributions. Identify and eliminate the anomaly values of observed data, so-called outliers, and choose the best, at least good discretization scheme in the parameter space to provide the optimal resolution according to having observed data uncertainty. We propose so-called blockwise parameter distribution approach. This concept includes such postulates. First, we divide the vectors of parameters and model data into blocks. Each block has an a priori probability distribution independent of the other block with the corresponding density. The probability densities in the data space correspond to the observed values of the block are also independent of each others. So the parameter blocks are independent and data block are independent. For each of the block of parameters and the data, the probability density can be of one of three types: Gaussian distribution, Laplace distributions, so-called long-tailed, and uniform distributions, so-called boxcar distribution. This process can be depicted by this such picture. The model connect. The model means the forward mapping G. Connect the parameter space to the data space, divided into several blocks of parameters and the data blocks. And the type of uncertainty types of uncertainty are like that. None means that there is no uncertainty. It corresponds to the Paul Dirac delta function. And other type of uncertainty is in the one-dimensional case, the graphs of probability density function can be depicted like this. And the basic theory of this approach have been developed. This basic theory consists of determining the residual function of the functionals and determining the obtaining the gradient vectors for optimization problems mentioned below. Gradient. For each types of the blocks, the gradient has been obtained. For the first problem, optimizations, it is very important to design the efficient optimization methods. One of the most usable methods for these purposes is steepest descent method. And these vectors also obtained by each type of considered blocks: Gaussian, long tail, and boxcar block. And the gradient methods for maximal posterior hypothesis can be written by like this. Fn is a precondition operator that can improve the properties of convergence of this process. Mu n is a step longitude. Gamma n is the steepest ascent vector. There are many proposals for Fn operator. For example, conjugate gradient methods. We use Fletcher-Reeves scheme, Pollack-Ribier, Henstel-Stiefel, Dai-Yuan, relatively variable matrix methods, Davidon, Fletcher-Power, Broyden-Fletcher-Goldfarb-Chenot, BFGS scheme, and Broyden scheme. To demonstrate the advantages of the method, we solved the problems for a Carolini packet that loaded by the uniform load on the top surface of the packet, and the data points where the data scanned from by the sensors are placed. We consider the packet with the axis of symmetry, the axis y, and the smoothly abutted border in the ground foundation. And the free stresses border like this. 3 problems can be solved using these methods. For example, specification of the data model uncertainty parameters, noisy Gaussian with the certain value of sigma d, and Laplace autocorrelation function. We consider data block with boxcar uncertainty with certain sigma, and in the parameters block also boxcar with certain sigma. It corresponds to the situation where the okay. The other part of our investigations is the localization of the outlier. In the certain point, in the point of the data, in this point, we use the artificial disturbance of the data with certain value, and see how it's influenced to the solution of the inverse problem. With using the boxcar block is not good, but with a long tail model for the data block, the localization of the outlier is easy to indicate in this point, and the value of disturbance also the simple to determine. In this picture, we can see the process of convergence into the to the point of maximal posterior hypothesis with a Gaussian block of parameter of data and the long tail block of parameters. In this picture, we can see that the numerical solutions is close to the analytical solutions for each the data on the top surface of the packet formed. Sensitivity of the solution quality to data noise. We use the data without noise and with the noise distributed by Gaussian law with some value of amplitude. For the low amplitude of the noise, the numerical solution is close to analytical solutions, and when the noise amplitude increases, the solutions will deteriorate. And in this picture, we may see the increase of the high frequency component of the noise during the solutions process of analysis process of inverse problem. And the problems is how to determine the optimal value of regularization parameters in the the sigma m plays the role of regularization parameters. These parameters we should choose like that the residual of the data can be split into two parts, CD and CM. And when is equal in order of magnitude, that's the appropriate value of the regularization parameter sigma m. And in this picture, we can see the influence of the choosing of regularization parameters into the approximate solutions. This case means excessive regularizations, excessive, that this solutions is close to a prior solution. The prior is the straight line x. In the pictures of the right, we see the solutions with insufficient regularizations and great disturbance, great amplifications of high frequency component. And in the center, we see the acceptable rate of regularization. The difficulty increases when the number of packets also increases. And in this picture, we see the conversion process to the optimization problem. And we will see that for the first layer, it is acceptable, and for the next layer, the boundary of interface is not very good. The second approach to solving the inverse, for analyzing the inverse problems, taking into account the Bayesian inference, is Markov chain Monte Carlo sampler. Named Metropolis-Hastings algorithm that was proposed in early 1950. In this algorithm, we can sample the posterior probability density, but by sampling the prior and using some process of switching to the next point and staying at the same point on the next iteration. For example, realizing this process to the two-layered packet is like that. Prior sampling and posterior sampling using the Metropolis-Hastings algorithms is like that. And the average of such set of the samples is like that, is very close to the analytical solutions. What is the difficulties by using MC methods? One main difficulty is the emptiness of the high-dimensional parameter space. In these pictures, we see the ratio of the volume of the inscribed hypersphere in the volume of the hypercube O1 by M. The space very fastly becomes void as the dimension of the space increases. And then it is very difficult to realize this algorithm, because in very in error cases the algorithms will stay to the same point, then to switch to the next point. It's very difficult problems of applying these algorithms. And at the end of this lections, we consider the perspective directions of the theory of inverse problems. First, the problem is to obtain the gradient of residual function. It's very difficult in a computational aspect. It requires a great number of computational works. And the common methods to solve these problems is to use so-called sensitivity function method and adjoint state methods for calculation this gradient. Multi-scaled and adaptive parameterizations. It is very important to use the optimal number of parameters of our inverse problem, because to avoid the phenomena like over-parameterizations or over-parameterization. Maximum projected curvature approach is the method to optimally determine the space in space mu m in gradient methods, the step longitude. In many programs, in many software, this step is very very difficult to determine this step. Then ensemble Kalman inversions means that we use the cloud of points in the space of parameter determined by sampling from prior probability density, and then we move this cloud of points to the close to the point of maximal posterior hypothesis. And also the behavior of this cloud can solve the problem of uncertainty propagation and uncertainty quantifications. Model learning methods can be used for this problem. also approximation of inverse problem solutions by surrogate models, for example, including the neural networks, is very perspective in our way. That's why, thank you for your attention. What is your questions? I see in the our chat these questions. I read now. What are the key advantages and limitations of employing the block-parametric approach in non-destructive control analysis for layered foundation, and how does it compare to the traditional methods in terms of accuracy and efficiency? Thank you for the questions. Comparing to the traditional methods, these methods make us possible to simplify the process of multi-scale and adaptive parametrizations to determine the optimal number of parameters and to use the several models. We can variate the several models, variating the number of blocks and parameters of blocks to obtain the flexible solutions. Flexibility is the main advantage of this approach. The next questions. In implementing the block-parametric approach for non-destructive control data analysis, how do you address potential challenges related to heterogeneous soil conditions and variable subsurface characteristics, and what strategies are employed to ensure the accurate interpretations of the data? Thank you for the questions. It's very interesting questions. Our problem is that where is our packet? The problem is the parameters of the media near to the data points is more or less good, and when the deeper the situation is worse. The main aim of the problem is to vary the different parameters of parameterization and data in order to simplify the analysis of obtaining the deeper part of the packet that is not close to the data surface where we collecting the data. The next questions. How does the block-parametric approach enhance the reliability and effectiveness of non-destructive control analysis, specifically tailored for layered foundation, and that advancement and innovation does not occur compared to conventional method. No, it's a similar questions. The main problems I have mentioned. Link attendance. I will see. The next, in the context of layered foundation, could you elaborate on how the block-parametric approach facilitates the identifications of distinct soiled layers, characterizations of their properties, and assessments of potential structures implications, and what considerations are crucial for its successful implementations in the real-world engineering scenarios. Very multi-aspect questions. Thank you. The main goal of the method is to determine the mechanical properties of the media that the layers consist of. For example, the elastic modulus and for Thorne ratio and other properties. If there is a weakness of this media, it reflects in the value of the, for example, elastic modulus. Our aim is to reliably identify the place of the when this weakness is appear, and it may appear in the deeper layers, deeper from the top surface where we collected the data. And our problem is to indicate the deeper, as deeper as we can, just as deeper as we can reach, like that. There is no questions in the chat. I don't see.
Yeah.
Thank you. Thank you.
Thank you so much. Yeah, I think it's very clear answer from Professor. Before I close this event, for our participant, please open your camera. I will take a picture on the count of 3. Okay, 1, 2, 3. Okay, another 1, 1, 2, 3.
I can
yeah?
I leave my email and research ID profile.
Yes.
In the chat.
Yeah. Yeah, sure.
That's my ResearchGate profile and my email. Okay.
Yeah, thank you so much. Yeah.
Yes, yes.
Yeah. Thank you so much for Mr. Olexander Trofimov for the wonderful information and sharing your knowledge. We hope this information will be beneficial for all participants. At least we hope to have more collaboration in the future with Oles Honchar Dnipro National University, Ukraine. For the visiting lecture today and here, we hope to see you soon. Thank you and have a nice day. Thank you so much for Mr. for sharing your contact person also. Yeah, thank you and goodbye.
Thank you, thank you. Glad to see you and glad to see to participate in your lectures.
Yes, thank you. Have a nice day.